This MIA module focuses on the PulseStormDillemma and how the mesoanalyst can play a role in improving threat targeting and messaging. Through this module, you will understand the challenges from pulse storms that make the current warning program somewhat problematic for communicating short-lived hazards. You'll learn about the environmental clues that suggest an increased probability for pulse severe storms and clusters. You'll learn about the radar signatures that differentiate severe from non-severe pulse storms, and you'll assess potentially better techniques for communicating pulse storm hazard threats compared to our existing convective warnings, especially for very small scale and marginal threats. Hi, I'm Pete Wolf in Jacksonville, Florida. So what is the PulseStormDillemma? Actually, it's a combination of issues that make it problematic for our convective warning program. You see, pulse storms don't behave the same way as our more reliable severe storms in stronger shear environments that are longer lived, more well behaved, more predictable, thus supporting longer warning lead times. Instead, threat areas tend to be very small in area and time, making it more challenging for our warnings. It can feel like you're playing whack-a-mole. You issue a warning for one cell, only to watch it quickly weaken while another cell quickly pops up, of course, outside of your polygon. In weak flow environments, the weak cell motion vector tends to be overwhelmed by the propagation vector as a result of new cell formation. So it can be challenging to accurately indicate where the threat will be in the next 20 to 30 minutes. It most likely will not be with the initial cell you warned for. The role of the mesoanalyst is more challenging for pulse storms, given the general uniform nature of the warm season environment where we have very weak shear. There's often little suggestion of lifting mechanisms that could support initiation. This module aims to help guide the mesoanalyst in terms of what to look for to best assist the warning and IDSS staff in targeting and communicating small-scale threats in time and space, while offering enough lead time to support the needs of decision makers. Pulse storms tend to occur as single cells and multi-cells. Single cell storms develop initially as a core aloft that descends to the surface. The intensity the storm reaches and the severity of the weather it produces often depends on how high that core develops and how much mass accumulates aloft before collapsing toward the ground. Severe pulse storms tend to develop higher aloft and tend to have greater mass, often reflected in higher reflectivity values and a taller and wider core, compared to non-severe pulse storms. Pulse multi-cell storms are particularly challenging. One intense storm can quickly weaken, followed by a new intensifying core in a matter of 1 or 2 radar scans, causing a warning for the initial cell to quickly become obsolete. As with single cells, pulse multi-cells tend to be more severe the higher the initial cores develop. Compared to single cells, pulse multi-cells have greater potential to become briefly severe as they produce boundaries that collide with each other, encouraging new, stronger updrafts. Whereas single cells generally produce single downbursts as the cells collapse, multi-cells can produce serial downbursts, one right after another with each subsequent cell within the multi-cell cluster, as shown in this reflectivity animation. There are multiple factors that make pulse storms challenging. First, a majority of these storms are non-severe, and a majority of those that do produce any damage are only marginally severe. It's rare to get a pulse storm that produces an 80 or 90 mile per hour downburst compared to getting one that produces a 50 or 60 mile per hour downburst. Take a look at this animation showing elevated cores from a large number of storms. Can you tell which ones will produce severe winds and which will produce strong but sub-severe winds? You'll likely need more information than just plan view reflectivity images to make that determination. In addition, pulse storms are short-lived. The severe threat may only last 10 to 20 minutes. By the time the storm develops a full core aloft that leads to a warning decision, impact may only be minutes away. Furthermore, getting the threat motion vector correct is difficult. Given weak flow aloft, the propagation vector, often along initiating boundaries, may be greater than the actual cell motion vector. How many different motion vectors do you see in this animation? Note a southward motion in northwest Georgia, westward motion in northeast Georgia, a few cells moving northwestward in western South Carolina, a variety of motions around Charlotte, North Carolina, and even some cells with very little motion, such as over the northwest corner of Georgia. Finally, when it comes to nowcasting the development of pulse severe storms, environments for significant pulse severe storms may not differ that much from those for strong but non-severe pulse storms. Here's a comparison of a significant northern Georgia event on August 1st, 2019 to basically a subsevere pulse storm event in central Florida on July 27th of 2020. Both have moist, unstable, weak shear environments. There are some subtle differences. The soundings are quite similar, perhaps a little more unstable for the severe case sounding, although by mid-afternoon, CAPE values appear similar for both, along with the downdraft CAPE values. The significant events tend to be associated with a weak shortwave rather than occur directly beneath an upper level ridge. Let's briefly look at how we might discriminate between severe and non-severe pulse storm environments using these two cases for illustration. So here is our August 1st, 2019 severe pulse storm event. Let's focus on the western portion of the Carolinas. We have fairly large CAPE values, decent downdraft CAPE values close to 1,000 joules per kilogram. The area of interest is within a precipitable water gradient with values below 2 inches. Soundings suggest favorable conditions for large differential theta E from the surface to mid-levels, including steeper low-level lapse rates and some drier air aloft. We also have a weak shortwave approaching the area with somewhat cooler 500 millibar temperatures near -9 Celsius. On this day, there were numerous severe weather reports across the mid-Atlantic region and the southeast. Now let's look at the non-severe pulse storm event in central Florida in July of 2020. Again, we have decent CAPE values, as we do most of the time in the summer in Florida. We have slightly lower downdraft CAPE values and not as much dry air aloft, with very high precipitable water values over the Florida peninsula with little gradient. This and slightly weaker lapse rate values likely mean lower differential theta E values from the surface to mid-levels. Central Florida is also directly beneath the upper ridge, with slightly warmer 500 millibar temperatures of -5 or -6 Celsius. I cannot say a pulse severe downburst is not possible in this environment. They can occur from time to time, but conditions would suggest subsevere winds would be more likely than winds of 60 miles per hour or greater. Other than a marginal wind damage report in northeast Florida, which could have resulted from subsevere winds, say 50 miles an hour, no severe weather was reported in central Florida from the storms that developed. So when it comes to environment conditions supporting pulse severe storms, think deep, intense updrafts that would promote elevated cores upon storm initiation, and cold downdrafts. What drives the wind are pressure perturbations within the storm, so we want a perturbation low at the surface beneath an intense updraft, and a perturbation high in the middle part of the core due to precipitation loading, and cooling due to melting ice or evaporation of in-train dry air. So for instability, we want very unstable environments, particularly large low-level CAPE and steep low-level lapse rates. For vertical shear, the weaker the better. What promotes buildup of mass aloft? Even a small amount of shear could evacuate mass at anvil level rather than building it up and thus building up the perturbation high within the core of the storm. For moisture, we favor anomalously high surface dew points and a good moist low levels, along with some drier air aloft. We want a cold downdraft, and that means larger surface to 700 or 500 millibar differential theta E values, or larger D-CAPE values. That's led by dry air aloft, steep lapse rates, and support for melting hail or entrained dry air that could lead to colder downdrafts, leading to stronger winds. So larger values of CAPE and D-CAPE, steeper lapse rates, larger differential theta E, and decent sources of lift, be it a shortwave aloft or outflow boundary collisions, favor greater severity of pulse storms. Whereas these conditions would support a higher centroid storm as viewed in cross-section, the conditions listed under non-severe would tend to support a lower centroid storm, which could still support 40 to 55 mile per hour wind gusts or small hail, but the probability of severe weather conditions would be considerably lower. Now let's turn to how we differentiate between detection of severe and non-severe pulse storms. Our focus will be on higher centroid versus lower centroid core development. Providing decent lead times through our convective warning program definitely works better with longer-lived severe convection than pulse severe storms. It can feel like a game of whack-a-mole trying to figure out which cells to warn and keeping up with the scan-to-scan changes. One cell could be severe on one scan, another one on the next scan. Take a look at this radar reflectivity animation with warning polygons overlaid for a good example. You can see the struggle to keep up with the changing hazards well north of Atlanta, Georgia, as well as near Charlotte, North Carolina. Often the result ends up being very large polygons that try to incorporate multiple potentially severe cells, ultimately leading to less useful and threat-specific information. Try answering this question. Is it true or false? Unfortunately, the answer is false. Trying to pinpoint hazard threats with very small polygons is a frustrating game. If you draw a small warning polygon for this storm, then you'll need another for this cell when it becomes severe, and potentially additional ones further west. Here's an example of the opposite approach, a 1-hour warning covering the whole area of storms. This large polygon is a good illustration of where there is potential for local severe storm development over the next hour. However, warnings are supposed to be for imminent or ongoing threats, which at this time only exists over a small percentage of the polygon. Note that the storm motion is just southwest at 10 miles per hour. Take a look at this question. Which of the choices shown do not appear before a damaging downburst occurs at the surface? There's only one correct answer here, and it is E, which is a signature that appears after the downburst strikes the surface and spreads out. This illustration shows how the evolution of severe versus non-severe pulse storms may differ. The severe cell tends to be a higher centroid one upon development, with much of the core above about 20,000 feet, representing a stronger updraft. Radar tends to suggest a core with more mass aloft than for a non-severe cell, which tends to have its centroid centered below 20,000 feet. The bottom illustration also shows that it's difficult to get much lead time if you wait to warn until the full core aloft develops and starts descending to the surface, as damaging winds may be occurring at the 20-minute mark. These illustrations differentiate between longer lead time cross-section signatures and zero lead time signatures. To get meaningful lead time, you essentially have to warn before the radar clearly shows an imminent severe threat. The best time may be sometime between formation of the high centroid cell and the development of a deeper core, typically in an inverted pyramid-like configuration, with a large amount of mass situated well above a more narrow base. Waiting until the core collapses and you see a divergent velocity signature near the surface can yield minimal lead time. Issuing the warning when the core aloft first appears can yield more lead time, but can also lead to a higher false alarm rate. How would you answer this question? Which signature in the list shown supports the longest potential warning lead time ahead of a downburst occurrence? The answer is A. The height of a storm core that initially forms indicates the likely intensity of the updraft. So in a highly favorable storm environment, one can target the higher initial cores as the storm's most likely to become severe with downburst winds. However, the false alarm risk is greater for A than waiting for signatures like those in D and E. Let's compare the radar signatures that offer at least short lead time to those that provide minimal lead time by the time you get the warning out. Frequently, warnings are issued after the velocity divergence signature appears at the surface, as the storm is collapsing, meaning the event has essentially already occurred. Why don't we have lightning jump on the short lead time list? We typically see this occur just as the core reaches its peak and starts to collapse. It generally offers very short lead time. It may be better to focus on a storm core jump, which can occur a radar scan or two ahead of the lightning jump, providing somewhat greater lead time. Which of these reflectivity cross-sections suggest favorable setups for severe downbursts, given a favorable storm environment? You're looking for a large amount of mass at a high elevation above the ground, thus a higher centroid storm. Thus, the best answers here are cross-sections B and D. Here's an important question to answer. What do you think? Now, obviously, the answer has to be yes, otherwise this module wouldn't be in the MIA course. The real benefit of the mesoanalyst is to help the radar and IDSS staff be proactive in threat communication and anticipate hazard occurrence as accurately as possible. Is that easy to do? Absolutely not. It's hard, especially when dealing with fairly uniform environments. But that's what brings satisfaction when you are successful. I often focus on initiating mechanisms to highlight where the probability for pulsed severe storms is most substantial. Here's an animation over northeast Florida on a typical summer day with pulse storms developing. It may seem random, but there is a pattern to where the warning polygons appear. Note the collisions of outflow boundaries and an outflow boundary with the east coast sea breeze, which initiate new, more intense convection, leading to minimal lead time warnings. Could the mesoanalyst help the IDSS person provide targeted threat information where conditions are most favorable for pulse storm development? Specifically, when and where these boundaries will collide. If you were the mesoanalyst, given a favorable environment for pulse severe storms, note the severe storms off to the east, where would you highlight new pulse storm development over the next 15 to 30 minute period? Note the boundaries about to collide within the blue rectangle. In this example, I would likely highlight this area. In fact, that's where a new severe cell developed. Thus, we provide greater lead time than waiting for signatures that lead to convective warnings, typically with minimal lead time. In this example, the warning came out just as the core was collapsing to the surface. While convective warnings may be our best tool to alert partners and the public to the potential for severe weather from longer-lived severe storms in stronger shear environments, are they the best tool for brief pulse storm threats? Consider that the warnings issued tend to be much larger than actual threat areas. Here's an example of a band of intense storms showing little motion. The black oval highlights the real threat area from these cells, but the polygon extends well to the south and east, perhaps to cover the threat of new cell development in these areas. Threat areas can also change rapidly. In this warning, what if you indicated a nearly stationary severe cell near Ossipee, but 20 minutes later a new severe cell develops near Burlington? Unless you issue an SVS to indicate this, you will not have notified Burlington of the new imminent threat. Finally, WarnGen does not make it easy to describe multiple severe storms within a given polygon. Typically, we use the line feature to cover multiple storms. I mentioned that dealing with the challenges of pulse severe storms can lead to fairly large warning polygons. Here's a rather extreme example with very large polygons covering very small scale threats. Let's zoom in on these polygons. The result can be less useful or even inaccurate information at times. Here's an example in which the warning correctly indicates a severe storm well south of Nashville in North Carolina, moving to the southwest at 10 miles per hour. The problem is they're moving away from the northern towns, including Nashville, that are shown in the polygon. Thus, those towns are alerted for no threat. The other warnings are for very small threat areas around the vicinity of Raleigh and also well west of Bunn. Although in this case, the storm is not exactly near Bunn. It is the closest community to the storm, and WarnGen uses it to indicate where the storm is near, even if it's not that close. These are examples of nearly stationary single cells, yet the polygons are alerting communities a large distance away from them. Let's focus on the Raleigh storm. From a customer perspective, which do you think is a better form of threat communication? for the pulse storm capable of producing downburst winds up to 60 miles per hour? Is it the warning, with a few minutes lead time, while providing a false alarm to a majority of the area warned, the best approach? Or would a longer lead time method of IDSS communication, such as a targeted social media threat graphic, or an NWS chat message to media partners ahead of the imminent threat signature, be a better approach? I'm not saying that we should not issue warnings here, but I'm asking what is the best approach when it comes to decision support for partners and the public. The radar person may only be able to achieve the warning approach with limited lead time, while the mesoanalyst could help the IDSS person construct a targeted threat message further in advance of the hazard. Here is another example. We have a pulse severe storm that has formed near Cliffside, North Carolina. WarnGen indicates that the storm is near Mooresboro, which it is not. The storm motion, based on the flow aloft, would suggest northeast at 5 miles per hour. So perhaps Mooresboro and Boiling Springs are in danger later in the warning period. But watch what happens over time. The propagation vector overwhelms the expected weak cell motion vector, leading to a net southward motion, resulting in a new warning polygon as it slips out of the original one. You can see how pulse storm operations can be frustrating. Would it be possible for the mesoanalyst to track boundaries with radar or satellite and try to anticipate that propagation to hopefully prevent the resulting frustration? Okay, let's try some cases, given what we've covered. We'll try a few forecasting cases as well as look at some individual cells to assess severe potential. Our first exercise will focus on a July day in northern Georgia. We expect pulse storms to develop, and SPC has general thunder across the southeastern U.S. on its 1630Z Day 1 outlook. The morning sounding shows a weak shear environment typical of the summertime across Georgia. It shows moderate lapse rates, some dry air aloft, but not a lot of CAPE. However, the morning visible satellite image shows full sunshine that will boost surface temperatures to near 90, yielding a steep low-level lapse rate, along with dew points in the lower 70s. As a result of a pooling of higher dew points in northern Georgia, the SPC mesoscale analysis page reveals an axis of higher surface-based and mixed-layer CAPE across that area. Note the sense of weak convergence with east to east-southeast flow over central Georgia and north to northeast flow at the surface over far northern Georgia. D-CAPE is not very high across the area. We also have a precipitable water gradient across northern Georgia. Aloft, there is a weak upper system over Georgia with cooler 500 millibar temperatures near -8 or -9 Celsius, which is also contributing to the larger CAPE values. So as the mesoanalyst, what would you brief your warning and IDSS staff concerning the potential for pulse severe storms this afternoon across northern Georgia? Did you come up with C as the correct answer? Clues to the potential for areas of more enhanced coverage of pulse severe storms would be a wave aloft, a sense of weak convergence and moisture pooling over northern Georgia, and a precipitable water gradient. Indeed, this was the focus area for intense pulse storms, producing numerous severe reports. Interestingly, a new microburst composite on the SPC mesoscale analysis page, which takes into account fields like surface-based CAPE, low-level lapse rates, precipitable water, and such, also indicated northern Georgia as a focus area for pulse severe storms, although it's uncertain how well this particular composite typically performs. Note that there are also large hail reports in northern Georgia. Going back to the sounding, do you see any shear in the hail growth region that could support particle separation, allowing hail to reach the ground despite such a warm environment? Yes, there is some shear in the mid-levels, between the 500 and 200 millibar levels. Thus, you might brief hail potential as well as downburst wind potential. Our next case takes us to another summer day, August 1st, 2019, across WFO Greenville, South Carolina's forecast area in the western portion of the Carolinas. Here are the observed morning soundings, typical for summertime in the southeast, with weak flow aloft, potential for decent CAPE and steep low-level lapse rates with heating, along with some drier air aloft, which could promote higher differential theta E. It's also fairly cool aloft for August, with 500 millibar temperatures near -10 Celsius. And that's the result of a weak upper trough over the area. Do you see any similarities with our first case? The SPC mesoscale analysis page shows an unstable environment by mid-afternoon, along with downdraft Cape values near 1,000 joules per kilogram. We also have medium values of precipitable water given some drier air well aloft, with a bit of a gradient over the western portion of the Carolinas. Given the data shown, what would be your expectation in terms of severe weather potential for the western portion of the Carolinas? Note that the Day 1 SPC outlook only has general thunder for the area. Does that change your perspective? It should not. SPC's focus is generally more significant events associated with stronger vertical shear rather than isolated pulse severe storm environments. In fact, there were a large number of wind and hail reports across the region. Once again, you'll see some mid-level shear on the sounding, suggesting potential for hail. Could the mesoanalyst play a role in trying to recognize days and patterns that may be more favorable for pulse severe storm environments? Okay, let's take a look at some cells in the region on August 1st. Here is one near Salem, North Carolina. We see the initial core formation 15 to 20,000 feet above the ground. Over time, it grows slightly to just above 20,000 feet. What product do you think might be best here? A severe thunderstorm warning for 60-mile-per-hour downburst winds, or perhaps something like an SPS or some other form of IDSS communication indicating 30 to 50-mile-per-hour winds? The lower height of the core suggests a somewhat weaker updraft, thus a weaker perturbation low near the surface, and the lack of a large core would suggest a lesser perturbation high aloft. This would be a typical storm that could produce 30 to 40 mile-per-hour wind gusts, maybe slightly higher as the core collapses. Try this cell southwest of Gaffney. It initially forms around 15,000 feet. The centroid grows vertically, centered here around 20,000 feet. What do you think? A warning at this point, or an SPS or other form of communication for subsevere wind gusts? We see greater mass on this scan, although all generally within the 10 to 20,000 foot layer. We see very high reflectivity values, indicative of melting ice, which can cool the downdraft. If the environment is really favorable, one might consider a warning, though non-severe winds in the 30 to 50 mile-per-hour range seem more likely. What about this cell? It has formed higher up than the prior two examples, centered between 20,000 and 30,000 feet above the ground, suggestive of a very intense updraft, leading to a strong perturbation pressure minimum near the surface. Over time, the cell grows downward as it starts to collapse, with little upward growth. Thus, it looks similar to the prior cell we dealt with, likely subsevere. But look, a new cell forms right next to it. What do you think about this one with a high reflectivity core in the 20 to 30,000 foot layer? If you don't choose a warning here, you might choose it on the next scan. Quite an impressive core aloft. A warning polygon now appears for this storm. We not only have a strong updraft, but a large mass aloft and possibly downdraft cooling due to melting ice, given the high reflectivity values. These support an intense downdraft, leading to a severe downburst. Now, why wouldn't you want to draw a tight warning polygon around the cell you see here at 0.5 degrees, given slow storm motion? Well, the new cell developing is actually aloft, and on the south side of Cliffside, which now appears as the core collapses to the surface. A small initial warning polygon might have missed this new, more intense cell to the south, thus requiring another warning polygon. Thus, you should not draw polygons based on 0.5 degree reflectivity. The next cell is southeast of Buchanan. This has a massive high centroid core within the 20,000 to 30,000 foot layer. You don't see it yet on 0.5 degree reflectivity. Would you warn for a severe downburst or issue another product for subsevere winds? Given the very high reflectivity values, suggesting melting ice, and the depth of this core, this likely has the stronger pressure perturbations and cooling from melting to support a severe downburst. Note the warning polygon appears as the core descends, leading to minimal lead time. Try this elevated core developing near Ossipee. Here is the initial cell developing. Anything to worry about? How about now? We have a high centroid core in the 20,000 to 30,000 plus layer. In a favorable environment, this might be the time to warn. Yikes. In this example, the warning doesn't appear until the core collapses, providing essentially minimal lead time for any downburst resulting during core collapse. Finally, try this cell that develops 15 to 20,000 feet above the ground. As it develops, it gradually increases in height into the 20 to 25,000 foot layer, but we already start seeing heavy precipitation reaching the ground. It likely does not have the vertical pressure perturbations needed to support a severe downburst, thus non-severe winds. Possibly in the 40 to 50 mile per hour range appear more likely. This storm had no warning and no reports. Let's try a different case, this time August of 2017 in Northeast Florida. The sounding reflects a typical Florida environment in the summertime with weak flow aloft, decent cape, potential for steep low-level lapse rates due to heating, some drier air aloft, D-cape values around 700 joules per kilogram, and precipitable water values near 2 inches. Near the time of storm development, the SPC mesoscale analysis page showed decent cape and D-cape values. Northeast Florida was beneath a ridge axis, with more westerly flow with weak waves passing to the north. Initial convective development was likely limited to that along sea breezes coming from the Gulf and Atlantic coasts. Take a look at this reflectivity animation. The Atlantic sea breeze is moving inland over the easternmost counties, and convection is occurring over Clay County, producing outflow boundaries. As the mesoanalyst, which of the 5 areas shown would you suggest highlighting for potential pulse severe initiation during the next 30 to 60 minute period? For area A, the sea breeze interacts with an outflow boundary from a storm to the north. For area B, there's potential for a sea breeze outflow boundary collision that could support more intense updrafts. For area C, there's potential for an outflow boundary collision from storms to the west and to the east. Now for areas D and E, with just single outflow boundary passage, we could see some strong cells, but likely lower severe potential at least initially. So I'd suggest the correct answers here are A, B, and C. Here, the mesoanalyst could encourage targeted threat messaging via a social media graphic or NWS chat post covering these 3 areas during the next hour. Would this support better decision making than just issuing warnings with less than 5 minutes lead time, or the confusion that can come from overlapping polygons as shown for the Clay County cluster of storms? Let's zoom in on the Clay County storm cluster animation with warning polygons overlaid. You can see the challenge of trying to keep up with the new convective cell development as outflows collide, leading to multiple overlapping polygons over the 2-hour period, mainly during the latter hour. This can get pretty confusing to customers. How might this be better messaged, supporting greater lead time, without the confusion of overlapping polygons, especially for a marginally severe hazard with winds up to 60 miles per hour? How about a targeted threat message, like the graphic shown here? Or the NWS chat message here, in advance of signatures suggesting an imminent wind threat? Would that contain greater value to decision makers than multiple overlapping warning polygons offering very short or no lead time? Again, I'm not suggesting no warnings here, but how might better information be offered from the IDSS person with help from the mesoanalyst? In summary, this module presented the challenges associated with the short-lived and erratic moving nature of pulse severe storms and clusters. It described the environmental fields to use for assessing severe weather potential from pulse storms and clusters. It described the radar signatures that differentiate severe from non-severe pulse storms, and that support at least short lead time. and it demonstrated potentially better techniques for communicating pulse storm hazard threats compared to our existing convective warnings. You have reached the learning assessment for this module, provided for your benefit. If you miss more than one of the questions, you are strongly encouraged to review this module again and retake the assessment. Good luck.